So let's begin reviewing this KSP test, which is really the 2001 AP Chemistry FRQ. I like the old tests. Okay. Any case, let's get right to it. They want to write, so number 1AI, write the equation for the dissociation of AgCl in water. I want the ionization reaction. So really important to write the phases here. So I'm going to take my silver chloride, and it's an ionic compound and a solid, and I'm going to write Ag plus ion, no big deal here, aqueous, plus the chloride ion. Now, I probably could get away with a double arrow here. I mean, this is going to be an equilibrium problem. So this is going to reach equilibrium, so we should have a double arrow there. In any case, that's my ionization reaction. And also careful, this is a nice easy one. It's a 1-to-1, but if there was of course, a subscript 2 right here, I would have to, of course, have a coefficient of 2 or some other number. Just be careful, it's not always going to be 1-to-1. So that should be straightforward. Okay, so now they want an I, a 1AI, they want you to calculate the solubility. What they're really talking about is the molar solubility. All right, so they sometimes say the solubility or the molar solubility, and anytime you hear that word, I always think of sol for X. All right, for the silver chloride. So they want you to solve for that. So very simply, what we need is we want the molarity. Okay, so let's go after it. Now, what they gave me in this question, they gave me how many grams actually did dissolve, and they gave me the amount of water. All right, so that's going to reach equilibrium. Not much actually did dissolve, so that should be very interesting there, that the Q reached equilibrium, okay, very quickly. All right, so we're going to continue with our formula here. We're going to solve for molarity. Just a reminder, molarity is just moles over liter. Now, a lot of questions in this area when they say solve for the molar solubility, okay, they actually give you the KSP and you have to solve for X. Okay, in this question, they gave you the grams. All right, and they just want you to understand what that value is at equilibrium. So let's go after. We need moles. So we're going to need a formula mass for silver chloride. So our formula mass is going to be, of course, we have 1 silver in the formula, and 1 times the atomic mass. If you go to your reference table, it's 107.87 grams per mole, and the chlorine, okay, is 35.453. I'm using the written values and not really rounding off here. You could certainly round off and get away with it, I think. 143.32, so that's the grams per mole. So we've got the formula mass, and I say formula because it's an ionic compound. It's not a molecule, but it's essentially the same way if you were solving for a molecular mass. Now we're going to go to get the actual moles, because that's, of course, what we need. So we're going to take the grams given, which is 8.9 times 10 to the negative 5, and that's grams of AgCl. And what we're going to do here, party people, is we're going to get rid of the grams, and we want a mole, so mole gets on the top, and we write our 143.32, and that's going to give us, that's going to give us some moles here, and that's going to give us 6.2 times 10 to the negative 5. And that's moles. And that's our top value. We're going to solve for the molarity, which is, of course, over liters, moles over liters. And they gave us 100 milliliters of water. That, of course, has to go 2 liters. Easy one there. And that is 0.1 liters, 0.100 liter. And even I can do this math in my head. So that's going to times it by 0.1. And it's going to gets smaller by a tenth, so our molarity is going to be, in this case, 6.2 times 10 to the negative 6. And that's equal to the concentration of AgCl. But it's also equal to the concentration of either what? Now, think about this, party people. It's either to this one, this ion, or this ion. Because as this breaks apart into equilibrium, for every one, okay, AgCl, there's one Ag plus and one chloride ion that's dissociates in that scenario. So they will be equal. And so when you solve for the X, as I always say, you'd be solving for either the one that dissociates into one, because for every one of these formulas, there's one of these ions. Okay. In any case, that is your answer right there. Put a little M there. Good thing to use your units when you can. All right, so that was a little bit different, except you used a little bit of mole concept there to get to those ends. All right, so now we're going to go to II Captain. They want you to calculate the value of the solubility product, KSP. So for this kind of question, we're going to need a equilibrium expression. So let's write that. So from our reaction above here, okay, from this reaction above, we're going to write KSP, which is equal to any type of KQ, all right, KC. It's got a bunch of different names, but it's products over reactants. Coefficients become exponents, and solids and liquids do not apply. So we're going to have this silver ions, brackets for molarity, times the chloride ions. And we have no denominator because solids and liquids do not apply. And here we are is with the solid. So that is our KSP value. And of course the coefficients are 1 apiece. So these are also 1. Careful, if there's a coefficient of 2 or more, you'd have to put that into right there, because coefficients become exponents in this example. So now what we're going to do is understand, we're going to solve for KSP, which is pretty darn simple, because what you need to understand is what we solved for was one of the concentrations of either one of these, and they have to be equal, okay? And if you don't see that, think about what we did earlier in the year, okay? We said water dissociated into an equilibrium. It broke apart into a proton aqueous and a hydroxide aqueous. And then we found something called Kw. Kw is an equilibrium constant, and we had this equation to understand pH. And I gave you this to be 10 to the negative 14. Well, what number times itself equals 10 to the negative 14? So in all actuality, that's x squared. To solve for either concentration, which would be the same because it's a 1 to 1 to 1, we'd square root both sides. So same idea here. And by the way, we got 1 times 10 to the negative 7, and then the negative log of that would give you a pH of 7. So all those things we've actually seen before. We're just applying it to a different equilibrium scenario. Concept is the same. So essentially what we got is x squared, because both of these are x. But we know what x squared is. We know it's equal to this value here. So let's go get it. So 6.2 times 10 to the negative 6 is equal to both of these. So I'm going to square that. And that, in this case, is going to equal my KSP. Very straightforward. So we've seen problems where they give you the KSP, and then you've got to solve for the actual x or 2x or whatever the coefficients are, or their stoichiometric relationships. Here it's x and x. So we're going the opposite way. There's only one way or the other. They either give you the KSP and solve for the x, or in this case, we were given this value and solving for KSP. So in any case, when we square this, okay, what we get is equal to 3.86 times 10 to the negative 11. And equilibrium values have no units, so you're safe there. So that, my friends, is your KSP. And by the way, it's very, very small, which means that this reaction barely goes forward. Remember, it's products over reactants. And so KSPs are types of equilibrium constants that express salts that aren't very good at dissolving. In fact, we would normally call these insoluble. We can actually measure how insoluble they are based upon their actual values of KSP. Okay, so we're going to move on to the next question here. And so now this question is, okay, now that we know what the KSP is, which is going to help us, they said at 25 degrees Celsius, which is a good to know the temperature because equilibrium constants like KSP are temperature sensitive. The value of KSP of lead chloride is 1.6, and the value for KSP for silver chloride is 1.8 times 10 to the negative 10. All right, so in this question, it's got nothing to do with what we just did. Okay, so this is silver chloride. So we're working to a new question altogether. Notice they gave me the KSPs for the two salts. Okay, and now they're saying if 60 milliliters of a 0.400 molar NaCl is added to a 60 milliliters 0.03 molar lead nitrate, will a precipitate form? Assume the volumes are additive and show calculations to support your answer. All right, so what are we doing here? And sometimes drawing helps. You have 60 milliliters of a 0.4 molar NaCl solution. So if it's helpful, maybe it is. Okay, there's my terribly drawn beaker. And what we have here is we have NaCl aqueous. Now we know that anything with a group 1 ion is completely soluble. So we're going to, if we're going to add sodium chloride, they're going to completely dissociate. And we know exactly how much based upon the milliliters and the molarity. Oh, I always think when I see milliliters and molarity, I think of molarity times volume in liters gives me moles, but that's just my thinking. Now, it's added to 60 milliliters of 0.03 molar lead nitrate. Now, we know something about lead nitrate. It's also soluble. Anything with a nitrate is completely soluble. Now, this is an old AP. In the new version, they don't make you know. You're not responsible for knowing your solubility rules. I would come out and say it. But in any case, we're delivering lead plus 2. Notice the 2 there. So we're going to add lead plus 2 here. Now we're also adding nitrates, but they're going to spectate. Okay, will a precipitate form? So if we're asking if a precipitate forms, we have to understand what precipitate we're talking about. And again, this is an older question, but I like it. I got to think about this. So what we're going to have is clearly lead chloride is insoluble. Okay, and we should know that because they're giving me a KSP for that. All right, and so I have that here. And I don't need this information because there's no silver. So this is probably for another question. So I'm going to use this. So I know it's pretty insoluble. So the lead is going to hit and collect or attract the lead chloride. It's going to make a precipitate, or possibly make a precipitate, depending upon if there is a Q that's less than K or greater than K. Yeah, this is a Q versus K question. And again, for those that haven't had me, I love to think about these questions in terms of these kind of U diagrams here. This would be the lead chloride that's from the KSP is insoluble, and this would be the free ions, lead plus 2, and the chloride ions. This would be your products. I'm drawing this diagram favoring the reactant, which is in this case the solid, okay, which is going to be in equilibrium with its ions at some point. So this would be the equilibrium position. It's the lowest position. It's the death of the reaction. And the question is, did we add enough ions to make it go what? Farther enough to reach this equilibrium position that favors the reactants? Or did we get past it? So is our Q in this position or is our Q in this position? And if you're getting confused, okay, we already know the KSP position. All right, the KSP position is equal to 1.6 times 10 to the negative 5. So what we're going to need to know is we mix these ions together. What is that snapshot in time for all these ions together? That's going to be your Q. So we're mixing two solutions together. And when you do that, we need to know what the new molarity is here. So we're going to have to use the dilution formula. Okay? So the dilution formula is MV equals MV. And so we took 60 milliliters, and we can keep this in milliliters here if you're going to use this proportion. And we have the molarity to be 0.04. And we want to know what the new molarity is. I'm going to use M because it stands for M, not an X. Okay. What's the new volume? Well, we're adding 60 to 60. The new volume is 120. Okay. And so when I do that, I get my new concentration to be 0.02 molar. Of course, that is my NaCl. Right, so that's NaCl. And now I'm going to do the lead Pb, well, the Pb plus 2 ion, I guess I could just keep it like that. And what's its original concentration? 0.03. It's 60 milliliters also. What's its new molarity when a new volume? Remember that 120 right there is the combined volume. I'm pouring two solutions together. So the molarities are getting diluted as their volumes increase. So what I do that is 0.03 times 60 divided by 120, and I get 0.015. And so that's going to be my new concentrations of my individual ions. Okay, so what is the overall reaction? I sort of alluded to it here. We should definitely write that in so we understand what's going on. So what we have here is we have lead chloride, and you should get in the habit anytime you're dealing with a salt dissolving and reaching equilibrium, get in the habit of writing the solid as the reactant. Because the KSP is written in this direction, we want the products to represent the ions here. So this is Pb plus 2, and that's aqueous. And this would be 2 chloride ions. Careful with that one. Okay, good times there. Now, how does this help me? Well, now I see this little 2 here. Okay, I need to write, okay, a Q value. Okay, now the Q equation is the same as the KSP or NEK. It's products over reactants, coefficients become exponents, and solids and liquids do not apply. So my friends, in chemistry, what we're going to do is do the Pb plus 2 times the chloride ion, and of course that gets a square. Okay, and now all I'm going to do now is plug in these values. Remember, equilibrium, we use either partial pressures if we're in a gas scenario, or we use molarities. Brackets are molarities. So I'm just going to plug these values in. So for the chloride ion, which is really the NaCl, okay, my molarity is 0.02 right there. And for my lead plus 2, it is 0.015. Okay. And so now we just do the math. And again, some people get confused like, hey, Mr. Grotsky, whoa. I learned that, let me just clean this up, being a little bit OCD here. So this would be 0.015. Some people say, Mr. Grotsky, shouldn't this always be 2x? Because now it's double? No. They just get whatever values they gave you. This is not at equilibrium. If we're measuring a solid, one of these, okay, breaking apart into one of these and two of these, yes. But they're just giving you an arbitrary amount. Based on those amounts, what is your Q there? So don't confuse pouring stuff together and things reaching equilibrium. You're right. If it does reach equilibrium, that value should be twice as much. But in any case, it's not, because we're just pouring stuff together. So what I get is, when I multiply that together, is I get my Q value, okay, which is my reaction quotient, to be 6.0 times 10 to the negative 6. So if Q is equal to, I guess I should write it over here, 6.0 times 10 to the negative 6. And what do we have here, party people? We've got our Q is smaller than our K. And therefore, if I'm smaller, that would mean that my Q is in this position. And what is it doing? It is working toward equilibrium and moving forward. So honestly, we haven't added enough ions in this case to have a Q position that's ahead. So my friends, this Q does not exist in head. So we would have a Q that's, Q is, in this case, less than K, and thus there is no precipitate. Okay, and that's all that meant. All right, so there we are with that question there. And so we assume the volumes are additive. So you would definitely get a point here for understanding we needed the dilution formula. You would definitely get a point for solving for the Q, and then you would get a point for recognizing the Q is less than K, and of course justifying or explaining what that means. So this goes forward. The solid is going to go what? Forward and dissolve, okay, because we just didn't have enough of these ions to shoot it past equilibrium and work backwards toward precipitation. So in any case, no precipitate there. On to the next question of this test. Okay, so in II, here we go. So we're in second half of this test here. Calculate the equilibrium value of lead plus 2 in a 1.0 liter of a saturated. Now, my friends in chemistry, the saturated PbCl2 is important. You say that word, and that means you're in equilibrium, right? That means that the solid, for a particular temperature, it has the greatest number of ions that it can dissociate into that water or that solution. And so if it's reached its maximum, that means if you add any more ions, some definitely have to go back and you've reached equilibrium. So it's another way of suggesting equilibrium is there. But they want the equilibrium value of the lead plus 2, okay, in a liter solution, to which 0.25 moles of sodium chloride has been added. So notice that group 1 ion. So sodium chloride is going to dissociate into Na+, and that's Cl negative, completely, because it's soluble. All group 1 ions completely dissociate. So essentially what we're doing is we are delivering the chloride ion, okay? We're delivering the chloride ion through the sodium ion, okay? And if we look at the reaction, let's write it again, okay? You don't have to for this question, but it's good to see what we're doing here. We have the solid PbCl2, solid, in equilibrium, double arrow, to its aqueous lead plus 2, and its chloride ion. Now it's PbCl2, so I really should put that there. Caught my own mistake if you were yelling at me. So PbCl2. Okay, and that means there's going to be 2 chloride ions, and that's aqueous again. Now, we know that the KSP from the previous questions is Pb plus 2 times the chloride ion squared. products over reactants, coefficients become exponents, solids and liquids do not apply. And of course, that solid means we have no denominator there, which is indicative how KSP expressions look like. This is called the law of mass action or the equilibrium expression, any case. So what they're saying to us is, hey, what is this concentration here? Remember, brackets mean molarity. If we have a common ion of chloride ions already there. And as I spoke to you about this in class, the best way to think about this is think about having the chloride ions in there and then dropping the salt, in this case the PbCl2. How much is this going to dissociate into Pb plus 2 and its chloride ions if there's already chloride ions there? It's always really cool and interesting, and I think most effective way to answer this is assume you have 100% of your solid, completely together before you see how far it goes forward. Okay, and because we're going to do some approximations here, and what we're going to do is very simply, when you see a common ion effect, the easiest way to solve this, okay, is to solve for this chemical, which is the X, and put the, well, this is not molarity, so I almost got caught here. It's moles. I've got to put the molarity in here of what we're adding. Now, this is an easy problem because molarity is moles over liter, and they say we had a 1 liter solution, so even I can do this math. So 1 liter solution, and I got 0.25. Okay, well, this is going to be 0.25 molar. Brackets means molarity. And our KSP, which we already established to be on the other page, to be 1.6 times 10 to the negative 5. And now we've got a very simple problem, except I've got to make sure that I remember the squared there. It's the biggest mistake people make. Remember that KSP is products over reactants, coefficients become exponents. So I can't forget to put that in there, as many people do, as I almost did. Okay, so we solve for X, okay, which is equal to the, Pb plus 2 ion concentration. And by the way, I'd be dividing by the square of 25, right? So if you need help with the algebra, I hope not, but 0.25 squared, okay, and then that's all that is, and you get the lead concentration to be 2.56 times 10 to the negative 4 molar. Okay, so that's the common ion effect. We had a common ion. Sodium has no effect because it's not part of this overall reaction. Right? So as you can see, there's no chlorine, but there is chlorine, and there's chlorine here, so there is definitely a common ion. And again, by approximations, it's just easier to start with the value already in here, and then drop the solid in, and always start with it undissociated. How far will this solid, okay, go? This is the solid, this is the ions. Okay, how far will it go until it reaches equilibrium? Okay, it's got to make some lead plus 2. Okay, and if you remember your acid base, if you have hydroxides are going up, this has got to go down. So really, very simple problem. People want to add and do the entire problem, but approximating away, okay, all of the other values makes this very simple. Okay, and again, the reason why I can approximate away, if we were doing an ice table, which, by the way, we're kind of circumventing the ice tables here because certainly these are really, really simple. Okay, so let's continue on to II, Captain. So this question is which one of these salts is going to precipitate first. So what do we have going on here is always good to draw if you have the time. So we're adding a sodium chloride solution to a beaker containing both silver nitrate and lead nitrate. Now nitrates are going to precipitate because they're very soluble. So we have lead plus 2 already in here. And we have silver plus. I'm getting that from the formula. There's 1 nitrate, -1, silver is +1. Nitrates are -1, lead is +2 if there's 2 of them. So you have those ions in here. Now, we're going to drop sodium chloride. And it's going to dissociate into Na+. And that's never going to attract other positives, right? So that doesn't make any sense. But it's going to dissociate into chloride ion. Ooh. And it's going to possibly make a precipitate. The question is, will it make the silver chloride precipitate? And they're telling you that. Or the lead chloride precipitate. Okay, so we're going to need to know their KSPs, and I think from previous problems we have that. So we're going to get on that right now. Okay, so what we're going to do is, in our previous problem, okay, now they're saying to us we have 0.12 molar silver nitrate and 0.15 molar. Okay, so we have the concentration, and we need to see if in the other problem, yes. So in B, if we remember this is II of B, so if we go back to the other page, okay, oops, I can't do it from this way. If we go back to the other page, they gave me the silver nitrate KSP. So let's go write the equation here. So silver chloride, they gave me the KSP for the silver chloride solution. Solid breaks apart into silver plus and chlorine negative. Okay. What would be the KSP here? Well, for the millionth time, it'd be products over reactants, coefficients become exponents, solids and liquids do not apply. I have that. And from the previous page, where it started with B, they said that the KSP was, for silver chloride, 1.8 times 10 to the negative 10. So 1.8 times 10 to the negative 10. Okay. And they gave us the concentration of the silver ion, okay, to be 0.12. And you say, wait a minute, they gave it for me for the silver nitrate, but that's the same for silver ion because it's completely soluble and there's 1 silver per formula. Okay, so we've got this. And then what we're going to do is we're going to solve for the chloride ion. And you say, well, why are we doing that? Well, we want to know what the concentration or the molarity of the chloride ion we have to actually have to reach equilibrium. And any value greater than that would cause a precipitation. Okay? For instance, if I do a U diagram of a salt breaking apart, here's, in this case, we'll do silver chloride. And here would be the 2 ions. These are the products. And this would be 100% of the solid, 100% of the ions. The K, of course, or in this case, the KSP, which is, same thing as KQ, just of this type of reaction, favors the reactant. That's why it's so small. Okay. Well, we're going to solve for, what the value of the chloride ion has to be when we reach the equilibrium, given that we have this much of silver already. Okay? And what that means is any value greater than that is going to take me into an area that's in this area where Q will be greater than what? Q will be greater than, Q is going to be greater than the KSP, and we would work this way. Okay? And that'd be, of course, working toward the solid and having it precipitate. So any value greater than that in this area is going to work backwards. So that'd be like our threshold. So in any case, when you solve for that, when we solve for X, or the concentration of the chloride ion, by just taking the KSP and dividing by 0.12 there, what do we get, party people? We get 1.5 times 10 to the negative 9. So the X, or the chloride ion concentration, is equal to 1.5 times 10 to the negative 9, which, that's the molarity. Brackets means molarity. So that means that any number greater than that is going to take me into this area here where Q is greater than K. SP or K, and we're going to work more spontaneously in reverse, which means we're going to make a solid and precipitate. Okay, so we're doing the same thing for the PbCl2, and again, I'm just going to rewrite this so you don't have to. You've done this in other parts of the test, but I'm just doing this right in front of me. Okay, and then I'm going to be Pb plus 2 aqueous plus 2 chlorides aqueous. And they could ask for the ionization reaction, and you should be able to put the solid, you should put the phases in, as well as the right stoichiometric coefficients. KSP, of course, is equal to the products over reactants. Coefficients become exponents. Solids and liquids do not apply. Oh, I'm going to put the aqueous there. Being a bad Grodsky right there. Okay, so we just need to start from scratch. So Pb plus 2. And I'll do this in blue. This time this is going to be the chloride ion, of course, squared because of the 2 there. All right, so we know the KSP from the previous page for lead chloride is 1.6 times 10 to the negative 5. All right, and the amount that they gave me in this problem was, 0.150 molar lead nitrate. So this would be 0.15, I got the 150. And again, we're solving for the chloride ion. Okay, but don't forget the squared. Okay, so algebraically, we're going to solve for what the chloride ion has to be to reach equilibrium, which really means any value bigger than that will cause the precipitation because the reverse reaction Q will be greater than K. Hopefully you get that now. So all I'm going to do mathematically is divide by 0.150 and square root both sides, right, to get rid of that. There's a little algebra there for your viewing displeasure. Okay. And when you do that, solve for x squared, you get the chloride ion concentration for this salt, for it, the threshold amount would be 1.0 times 10 to the negative 2 molar. So what does this mean? Well, as we pour sodium chloride, which means we're just adding more chloride ions, which threshold is going to be met first? Is it going to be the 1.5 times 10 negative 9 or the 1.0 times 10 to the negative 2? Well, who's the smaller number? Now, why does a smaller number work? Because I'm pouring chloride in. It's starting at, from a theoretical 0, and it increases as I add more and more chloride ions. So which number am I going to hit first as the chloride ion concentration increases by the addition of the sodium chloride? Well, it's going to be the smaller number. It's going to take a lot more chlorides to be added for this to reach the threshold. So that tells me that silver chloride is going to precipitate first, because when the chloride concentration, or it requires a much smaller chloride ion concentration in order for its Q to be bigger than K and cause the what? The precipitation or the reverse reaction to be more spontaneous. So that's the answer. So that's how you do those problems. I hope that helped. They're not terribly difficult. The math is easy. Of course, what the math means more. But with practice, you'll see that, wow, I want to see these problems. Okay? So hope that helped. Good luck and take care.